Here we have a model of a 12-story building. The building structure is primarily reinforced concrete, but we can see that one of the facades is made of steel. This hybrid structure can present challenges for response spectrum analysis, since we may want to account for different damping ratios depending on the materials. Let's now review the damping data used for the response spectrum analysis of this model. We can see that the response spectrum function was designed for a damping ratio of 5% of critical. It's very important to note that this value does not directly change the generated spectrum function. It only serves as an indication to the response spectrum load case that this function was created for that damping ratio. In other words, changing this value here does not modify the spectrum ordinates, it only indicates that the function was calculated for a different damping ratio. Now let's check how damping is defined for the response spectrum analysis. We can see that we are requesting 5% of critical damping for all modes. It's important to emphasize that this damping is added to all other sources of damping in the model. By default, material damping is set to 0. Therefore, we should expect 5% damping for all modes if there are no links with damping properties. Let's now look at some vibration modes of the structure. Mode 1 is primarily in the direction perpendicular to the steel facade, so its damping is expected to be governed mainly by the concrete structure. Mode 2 only twists the steel facade, without deforming it along its stiffness direction. So again, this mode is expected to be governed primarily by the concrete structure. Now, in Mode 3, we see significant deformation of the steel structure in its plane, so this mode is expected to be influenced by the steel damping. Let's now check the calculated damping for each mode and the corresponding accelerations. In this case, we obtain a damping value of 5% of critical for all modes, including Mode 3. If the damping matches the value for which the spectrum function was calculated, the accelerations will correspond exactly to the spectrum ordinates. Now let's try to solve the problem by considering 2% critical damping for the steel structure and 5% for the reinforced concrete structure. We could inspect the mode shapes and assign different damping values to each mode based on material deformation. However, that would be very time-consuming and would need to be adjusted every time the model changes. The solution is to activate material damping instead of assigning damping to individual modes. Let's unlock the model and make the necessary changes. First, let's go to the concrete material used throughout the structure. As mentioned earlier, it currently has 0 damping, which we will now change to 5%. Now we do the same for the steel material. In this case, we assign a value of 2%. Very important, we need to change the damping defined in the response spectrum load case, because this value will be added to all modes. If we leave it as is, a mode governed by reinforced concrete would end up with nearly 10% damping, which is the sum of this value and the concrete material damping. We can now run the analysis again. And now we can check the damping calculated for each mode. We see that Mode 3 has a much lower damping than 5%, because it has significant participation from the steel structure, which has only 2% damping. The same happens for Modes 6 and 10. Now we can place the table obtained with the previous model on the left and compare the results. We clearly see that the accelerations for Modes 3, 6, and 10 have been amplified. This is because the calculated damping is lower than the damping for which the spectrum function was generated.